Welcome to this problem walkthrough. Today, we'll be diving into problem number 1057, Campus Bikes. In this problem, we'll explore how to efficiently assign bikes to workers based on their Manhattan distances. Let's get started. In this problem, we have a 2D grid where M workers and N bikes are located at specific points. The workers are represented by their positions in the workers array, and the bikes are represented by their positions in the bikes array. The task is to assign a bike to each worker in such a way that no two workers share the same bike, and no bike is assigned to more than one worker. The objective is to minimize the sum of the Manhattan distances between each worker and their assigned bike. The Manhattan distance between 2 points is calculated as the sum of the absolute differences of their x-coordinates and y-coordinates. Once the bikes are assigned, we need to return an array where each element represents the index of the bike assigned to the corresponding worker. If there are ties in the assignments, we resolve them by prioritizing the smallest worker index, and if there's still a tie, we choose the smallest bike index. The output of the problem is a list of integers where each index corresponds to a worker, and the value at that index is the index of the assigned bike. Let's look at an example. Suppose workers is 0, 0, 2, 1, and bikes is 1, 2, 3, 3. The output should be 0, 1. Here's why: worker 0 is located at 0, 0, and worker 1 at 2, 1. Bike 0 is at 1, 2, and bike 1 at 3, 3. We need to determine the best assignments of bikes to workers while minimizing the total Manhattan distance. To calculate the Manhattan distances, we evaluate each worker-bike pair. For worker 0, the distance to bike 0 is 0, 1 plus 0, 2 equals 3. And the distance to bike 1 is 0, 3 plus 0, 3 equals 6. For worker 1, the distance to bike 0 is 2, 1 plus 1, 2 equals 2, and the distance to bike 1 is 2, 3 plus 1, 3 equals 3. Based on these distances, worker 0 is assigned to bike 0 because it has the smallest distance of 3, and worker 1 is assigned to bike 1 because it minimizes the distance for the remaining worker. This results in the output 0, 1. Another example has workers equals 0, 0, 1, 1, 2, 0, and bikes equals 1, 0, 2, 2, 2, 1, where the output is 0, 2, 1. In the second example, worker 0 is at 0, 0, worker 1 is at 1, 1, and worker 2 is at 2, 0. The bikes are located at 1, 0, 2, 2, and 2, 1. Let's compute the Manhattan distances. Worker 0 has distances of 1 to bike 0, 4 to bike 1, and 3 to bike 2. Worker 1 has distances of 1 to bike 0, 2 to bike 1, and 2 to bike 2. Worker 2 has distances of 1 to bike 0, 2 to bike 1, and 1 to bike 2. Based on these distances, we assign bike 0 to worker 0 since it minimizes the distance. Then, bike 2 is assigned to worker 1, and finally, bike 1 is assigned to worker 2. This gives the result 0, 2, 1. Now, let's discuss some important constraints and edge cases. First, the number of workers and bikes can go up to 1,000, so the solution must be efficient to handle large inputs. Each worker and bike position is a pair of integers between 0 and 10^3. For edge cases, if there is only one worker and one bike, the result is straightforwardly 0. If there are multiple workers but only one bike, the bike is always assigned to the worker with the smallest index. When a worker and a bike are located at the same position, their Manhattan distance is 0, making it the preferred assignment. Finally, the solution should handle large inputs efficiently, ensuring that both time and space complexity are well optimized for the given constraints. To begin solving the campus bikes problem, we can first consider the brute force approach. The intuition behind this method is straightforward. We calculate the Manhattan distance between every worker-bike pair, sort these pairs by distance, and then assign bikes to workers based on the sorted order. For each worker, we assign the closest available bike, ensuring no bike is assigned more than once. The Manhattan distance, which measures the grid-based distance between 2 points, is computed as the absolute difference between their x-coordinates added to the absolute difference between their y-coordinates. By sorting the worker-bike pairs, we can prioritize the smallest distances first. The algorithm involves three main steps. First, compute all possible distances for the m workers and n bikes. Second, store these distances along with their corresponding worker and bike indices. And third, sort the distances by ascending order of distance, and in cases of ties, by worker and bike indices. Finally, we iterate through the sorted list, assigning bikes to workers while marking assigned bikes as unavailable. This ensures that each worker gets the closest possible bike available at the time of assignment. The brute force approach, while effective for small datasets, has significant drawbacks in terms of efficiency. The time complexity is dominated by the sorting step, which takes O, m*n*log, m*n, for all worker bike distances, where m is the number of workers and n is the number of bikes. Additionally, the space complexity is O, m*n, as we store all worker bike pairs along with their distances. These requirements make the brute force approach impractical for scenarios with a large number of workers or bikes. To address these inefficiencies, we can use an optimized approach centered around bucket sorting. The key insight here is that the maximum possible Manhattan distance is bounded by the size of the grid, which allows us to group worker bike pairs into buckets indexed by their distances. This eliminates the need for explicit sorting. By processing pairs in the order of their distances, we achieve the same prioritization as sorting but with reduced computational overhead. Importantly, the bounded nature of Manhattan distances ensures that the number of buckets remains manageable, even for large grids. The optimized bucket sort approach involves a few key steps. First, we compute the Manhattan distances between all worker bike pairs, just as in the brute force approach. However, instead of storing these pairs in a single list to be sorted, we place them into buckets, where each bucket corresponds to a specific Manhattan distance. For example, all pairs with a distance of 1 go into the first bucket, pairs with a distance of 2 into the second bucket, and so on. Once the distances are bucketed, we process these buckets in ascending order of distance. For each bucket, we iterate through the worker bike pairs, assigning bikes to workers if both the worker and the bike are available. If a worker already has a bike or the bike is already assigned, we skip the pair. This process continues until all workers have been assigned bikes. The bucket sort approach significantly improves efficiency. The time complexity is reduced to O, m*n, as we avoid the explicitly expensive sorting step, and the space complexity remains O, m*n, as we still store all pairs but in a structured, bucket format. This method is especially advantageous for large grids, as the maximum number of buckets is bounded by the grid dimensions. After evaluating both approaches, the bucket sort optimization stands out as the better strategy for solving this problem. While the brute force method is conceptually simpler and easier to implement, its reliance on sorting introduces significant computational overhead, making it inefficient for larger inputs. On the other hand, the bucket sort technique leverages the bounded nature of Manhattan distances to avoid sorting altogether, resulting in a faster and more scalable solution. This approach is particularly well suited for scenarios with a large number of workers and bikes, as it processes pairs efficiently without being impacted by the size of the grid. In terms of trade-offs, the brute force approach is simpler in design but limited in scalability, whereas the bucket sort method requires careful bucket management but offers superior performance. Given the constraints of the campus bikes problem, the bucket sort optimization is the ideal choice, balancing efficiency with practical implementation requirements. In this problem, we are tasked with assigning bikes to workers in such a way that the total sum of Manhattan distances between the assigned worker bike pairs is minimized. The constraints are straightforward: each worker can only be assigned one bike, and each bike can only be assigned to one worker. To start, we define the problem space. The input consists of two lists, one for worker coordinates and one for bike coordinates. For example, workers might look like x1, y1, x2, y2, and bikes might look similar. The output we aim to produce is an array where each element gives the index of the bike assigned to a worker. The next step is to compute all possible worker bike distances. We use the Manhattan distance formula, which is the absolute difference in the x-coordinates plus the absolute difference in the y-coordinates. For every worker bike pair, we calculate and store the distance along with the indices of the worker and bike as a tuple. This allows us to create a structured dataset that can later be sorted for prioritizing assignments effectively. Once we have all the distance pairs, the next step is to sort them. We sort these tuples first by the distance in ascending order. If two pairs have the same distance, we resolve ties by sorting by worker index, and if there's still a tie, by bike index. This ensures that the closest worker-bike pairs are considered first, while maintaining a consistent and deterministic order. The time complexity for sorting all these pairs is O, m*n*log, m*n*, where m is the number of workers and n is the number of bikes. After sorting, we proceed with a greedy approach to assign bikes to workers. To handle this, we use two sets, assigned _workers to track workers who have already received a bike, and assigned _bikes to track bikes that have already been assigned. We then iterate through the sorted list of distance pairs. For each pair, if both the worker and bike are unassigned, we assign the bike to the worker and mark them as assigned. This process continues until all workers have been assigned bikes. This greedy method ensures that we always select the closest available worker-bike pair, aligning with our goal of minimizing the total distance. After completing the assignments, we construct the result array. This array, assignments, is indexed by workers, so the value at index I corresponds to the bike assigned to worker I. The sorting step ensures that we process distances in ascending order, which directly helps minimize the total distance. By using a greedy approach, we efficiently allocate bikes while adhering to the constraints that each worker and each bike can only be assigned once. A few edge cases to consider include situations where there are more workers than bikes. In such cases, some workers may remain unassigned, though the problem typically assumes there are at least as many bikes as workers. Another edge case involves ties, where multiple worker-bike pairs have the same distance. Here, the secondary and tertiary sorting criteria of worker index and bike index ensure a deterministic solution. The algorithm relies on specific data structures. We use a list of tuples to store distances for efficient sorting, sets to track assignments with constant time updates, and the result array to store the final output. Analyzing the complexity of the algorithm, we start with the computation of all distances. This step involves calculating the Manhattan distance for every worker-bike pair, leading to a time complexity of O, m*n*. Next, the sorting step dominates the overall complexity. Sorting the distance pairs takes O, m*n*log, m*n*, which is the most computationally expensive part of the algorithm. Finally, the greedy assignment process involves iterating through the sorted pairs, which has a complexity of O, m*n in the worst case. Combining these, the overall time complexity is determined by the sorting step, giving us O, m*n*log, m*n. To optimize the algorithm, we could use a priority queue to process the smallest distances first, avoiding the need to store and sort all distance pairs at once. This would reduce memory overhead and improve runtime for sparse datasets. Additionally, we can terminate the iteration early once all workers have been assigned, saving unnecessary processing. Let's walk through an example to solidify our understanding. Suppose we have two workers located at 0, 0, and 2, 1, and two bikes located at 1, 2, and 3, 3. First, we compute the distances. Worker 0 to bike 0 has a distance of 3, and to bike 1 has a distance of 6. Worker 1 to bike 0 has a distance of 2, and to bike 1 has a distance of 3. This gives us the distance pairs 3, 0, 0, 6, 0, 1, 2, 1, 0, 3, 1, 1. Sorting these pairs results in 2, 1, 0, 3, 0, 0, 3, 1, 1, 6, 0, 1. Now, we assign bikes. The first pair, 2, 1, 0, assigns bike 0 to worker 1. The next pair, 3, 0, 0, assigns bike 1 to worker 0. At this point, all workers have been assigned bikes, so we stop. The final result is 1, 0, meaning worker 0 gets bike 1, and worker 1 gets bike 0. The final output of the algorithm is the array 1, 0. This tells us that worker 0 is assigned to bike 1, and worker 1 is assigned to bike 0. By following the outlined steps, computing distances, sorting pairs, and assigning bikes greedily, we ensure that the total Manhattan distance is minimized while respecting the one-to-one assignment constraints. This example demonstrates the efficiency and correctness of the algorithm. This solution addresses the LeetCode problem number 1057 campus bikes using a greedy approach. The goal is to assign bikes to workers such that the total Manhattan distance between assigned pairs is minimized. The first step is to calculate all possible worker-bike pairs along with their Manhattan distances. The distance is computed as abs, worker, 0, bike, 0, plus abs, worker, 1, bike, 1. Each pair is stored as a tuple, distance, worker_index, bike_index. Next, the list of pairs is sorted in ascending order, first by distance, then by worker index, and finally by bike index. This ensures that the smallest distance pairs are prioritized, and ties are resolved based on worker and bike indices. The algorithm then initializes a result list with -1 for all workers, indicating that no workers have been assigned bikes initially. A set assigned _bikes is used to keep track of bikes that have already been assigned. The algorithm iterates through the sorted list of pairs. If a worker does not yet have a bike and the bike is not already assigned to another worker, the bike is assigned to the worker, and the bike is marked as used. This process continues until all workers are assigned bikes. Finally, the result list, which contains the assigned bike indices for each worker, is returned. This solution is efficient due to the sorting step, and the greedy assignment ensures correctness, making it suitable for competitive programming scenarios like LeetCode. Here, we begin implementing the solution by importing necessary packages and defining our class and method. The assignBikes method takes two 2D arrays as input, one for workers' positions and another for bikes' positions. To solve the problem, we first create a list called pairs to store all possible worker-bike pairs along with their Manhattan distances. The Manhattan distance is calculated as the sum of the absolute differences of the x and y coordinates between a worker and a bike. By using nested loops, we iterate over each worker and each bike, calculate the distance, and add an array containing the distance, worker index, and bike index to the pairs list. Once we have all the pairs, we sort this list based on 3 criteria, first by distance in ascending order, then by worker index, and finally by bike index. This ensures that we prioritize the closest available bike for each worker, and if distances are tied, we resolve them in a consistent order. Finally, we initialize a result array to store the bike assignments for each worker, where the index represents the worker and the value will represent their assigned bike. We then fill the result array with -1 to indicate that no worker has been assigned a bike yet. Additionally, we create a set called assigned bikes to keep track of the bikes that have already been assigned. Next, we iterate through the sorted pairs list, which contains all possible worker-bike pairs ordered by distance and priority. For each pair, we extract the worker and bike indices. If the current worker has not yet been assigned a bike, and the bike is not already in the assigned bike set, we assign this bike to the worker by updating the result array and adding the bike to the set of assigned bikes. This ensures that each worker gets the closest possible available bike while preventing any bike from being assigned to multiple workers. After processing all pairs, we return the result array, which contains the final bike assignments for all workers. In this problem, we aim to assign bikes to workers on a 2D grid in a way that minimizes the Manhattan distance for each assignment. Each worker must be assigned exactly one bike, and no bike can be assigned to multiple workers. To break ties, we prioritize assignments by worker index first and then by bike index. For example, given the workers at coordinates 0, 0, 2, 1, and bikes at 1, 2, 3, 3, we start by computing the Manhattan distances for all worker-bike pairs. The distances are calculated as follows: worker 0 to bike 0 is 3, worker 0 to bike 1 is 6, worker 1 to bike 0 is 2, and worker 1 to bike 1 is 3. These distances are key to determining the optimal assignments. We then create a list of all worker-bike pairs along with their respective distances: 3, 0, 0, 6, 0, 1, 2, 1, 0, 3, 1, 1. To efficiently process these pairs, we sort them in ascending order based on distance, and in the case of ties, by worker index and then bike index. The sorted list becomes 2, 1, 0, 3, 0, 0, 3, 1, 1, 6, 0, 1. Now we assign bikes following this order. The first pair, 2, 1, 0, assigns bike 0 to worker 1, updating the result to -1, 0, with bike 0 marked as assigned. The next pair, 3, 0, 0, attempts to assign bike 0 to worker 0, but since bike 0 is already taken, we proceed. Similarly, pair 3, 1, 1 has no effect as worker 1 already has a bike. Finally, pair 6, 0, 1 assigns bike 1 to worker 0, resulting in 1, 0, with both bikes assigned. The final output for this example is 1, 0, indicating that worker 0 is assigned bike 1 and worker 1 is assigned bike 0. Next, let's consider a second example with workers at 0, 0, 1, 1, 2, 0, and bikes at 1, 0, 2, 2, 2, 1. We compute the Manhattan distances for all worker bike pairs. Worker 0 to bike 0 is 1, to bike 1 is 4, and to bike 2 is 3. Worker 1 to bike 0 is 1, to bike 1 is 2, and to bike 2 is 1. Worker 2 to bike 0 is 1, to bike 1 is 2, and to bike 2 is 1. These distances give us a comprehensive list of all possible assignments and their costs. The pairs list for this example is 1, 0, 0, 4, 0, 1, 3, 0, 2, 1, 1, 0, 2, 1, 1, 1, 1, 2, 1, 2, 0, 2, 2, 1, 1, 2, 2. Sorting these pairs results in 1, 0, 0, 1, 1, 0, 1, 1, 2, 1, 2, 0, 1, 2, 2, 2, 1, 1, 2, 2, 1, 3, 0, 2, 4, 0, 1. Now we begin assigning bikes. The first pair, 1, 0, 0, assigns bike 0 to worker 0, updating the result to 0, -1, -1, with bike 0 marked as assigned. The next pair, 1, 1, 0, is skipped since bike 0 is already taken. The third pair, 1, 1, 2, assigns bike 2 to worker 1, resulting in 0, 2, -1, with bikes 0 and 2 marked as assigned. Finally, the fourth pair, 1, 2, 0, is skipped as bike 0 is already assigned. Continuing from the sorted list, we encounter pair 1, 2, 2, which is skipped since bike 2 is already assigned. The pair 2, 1, 1 is also skipped because worker 1 already has a bike. Next, pair 2, 2, 1 assigns bike 1 to worker 2, completing the assignment as 0, 2, 1, with all bikes now assigned. This solution ensures that each worker is assigned a bike while minimizing the total Manhattan distance. The final output for this example is 0, 2, 1, where worker 0 gets bike 0, worker 1 gets bike 2, and worker 2 gets bike 1. In the third example, we have a single worker at 0, 0, and 2 bikes at 1, 1, 2, 2. The Manhattan distances are computed as follows: worker 0 to bike 0 is 2, and worker 0 to bike 1 is 4. These distances give us the pairs list, 2, 0, 0, 4, 0, 1. Since the pairs are already sorted by distance, worker index, and bike index, we don't need to sort further. Now we assign bikes starting with the first pair, 2, 0, 0, which assigns bike 0 to worker 0, updating the result to 0, and marking bike 0 as assigned. The second pair, 4, 0, 1, is skipped since worker 0 already has a bike. The final output for this example is 0, indicating that worker 0 is assigned bike 0. This demonstrates how the algorithm handles cases with fewer workers and bikes, ensuring correctness and efficiency regardless of input size. By systematically computing distances, sorting pairs, and assigning bikes, we achieve optimal assignments in all scenarios. To analyze the time complexity of this solution, we break it into 3 main steps. First, we generate all possible worker-bike pairs. For each of the n workers, we iterate through the m bikes. Calculating the Manhattan distance for each pair is a constant time operation, so generating the entire pairs list takes n*m. Next, we sort the pairs list. Since it contains n*m elements, sorting it with an efficient algorithm like timsort requires n*m*log n*m time. Finally, we assign bikes to workers by iterating through the sorted pairs list. In the worst case, we process all n*m pairs, performing constant time checks and assignments for each. This step adds another n*m to the complexity. When we combine these steps, the sorting operation dominates, giving the overall time complexity of the solution as n*m*log n*m. The overall time complexity of the solution is n*m*log n*m, as sorting the pairs list is the most time-consuming step. Now, let's look at the space complexity. First, we need to store the pairs list, which holds all possible worker-bike pairs and their distances, requiring n*m space. Next, the result array stores the assigned bike for each worker. Since there are n workers, this takes n space. Additionally, we use a set called assigned_bikes to track which bikes have already been assigned. In the worst case, when all m bikes are assigned, this set requires m space. Finally, the sorting process may require auxiliary space. Python's timsort algorithm, for example, has a worst-case auxiliary space complexity of n*m. When we sum these components, the overall space complexity of the solution is n*m. The overall space complexity of this solution is n*m. Let's compare this approach to a brute force method. A naive approach would involve trying all possible permutations of worker bike assignments and calculating the total distance for each. For n workers and m bikes, this would involve m permutations if m is greater than or equal to n, and we'd need to compute the distance for each assignment. This quickly becomes computationally infeasible as the input size grows. In contrast, the current solution optimizes this process by reducing the problem to sorting a list of all possible pairs. By assigning bikes greedily based on the sorted list, we ensure correctness while limiting the time complexity to n*m*log n*m, a significant improvement over the factorial time complexity of the brute force approach. Let's analyze the best, average, and worst-case scenarios for this solution. In the best case, we still need to calculate the distances for all worker bike pairs and sort the list, so the best case complexity remains n*m*log n*m. Similarly, the average case shares the same complexity because the algorithm always processes all pairs and performs a sort regardless of how the input data is structured. Lastly, the worst-case complexity is also n*m*log n*m, as the sorting step dominates the runtime in all scenarios. Since the algorithm consistently follows the same steps for any input, the time complexity remains the same across best, average, and worst cases, ensuring predictable performance regardless of input distribution. When solving this problem, there are several common mistakes to watch out for. First, failing to handle ties and the Manhattan distance properly can result in incorrect assignments. Remember, the problem specifies that if two worker bike pairs have the same distance, you must prioritize the worker with the smaller index, and if there's still a tie, the bike with the smaller index. Your sorting logic must respect these tie-breaking rules. Next, be mindful of the efficiency of your sorting or comparison logic. Sorting all possible worker bike pairs without optimization can lead to time complexities as high as n²*log n, which becomes impractical for larger inputs. Consider using alternative methods like priority queues to process pairs dynamically. Another issue to avoid is confusing worker bike assignments. For example, if you reassign a bike that's already been assigned or fail to track which workers are matched, your solution will break. Using visited sets or similar bookkeeping techniques can help you keep track of assignments effectively. Lastly, avoid making assumptions about fixed dimensions or constraints, such as the grid size or number of workers and bikes. These assumptions can cause your solution to fail edge cases, so ensure your implementation handles varying input sizes flexibly and reliably. Another critical mistake to avoid involves the implementation of the Manhattan distance formula itself. The formula x1 x2 plus y1 y2 may seem simple, but errors can arise from incorrect coordinate indexing or sign handling. Always double-check your calculations to ensure they're accurate. Now, let's discuss some key insights for interviews. This problem is an excellent opportunity to demonstrate your ability to balance correctness and efficiency. Start by presenting a brute force approach to establish a baseline, and then discuss how you would optimize it, perhaps using greedy strategies or priority queues. Sorting-based solutions are valid, but you must handle tie-breaking rigorously, as interviewers often focus on edge case handling. Additionally, scalability is a key discussion point. Be prepared to explain trade-offs in time complexity, such as comparing sorting-based approaches with heap-based solutions, and how these impact implementation complexity. Finally, clarity in your thought process is crucial. Clearly articulate how you handle tie-breaking rules, keep track of assignments, and address edge cases. This will demonstrate not only your technical skills but also your ability to communicate effectively. This problem is closely related to other assignment and optimization problems, which can provide valuable practice. The original problem, LeetCode 1057, focuses on assigning workers to bikes based on Manhattan distance. LeetCode 1386 Cinema Seat Allocation involves a similar concept of making assignments under constraints with specific tie-breaking rules. LeetCode 857 Minimum Cost to Hire K Workers is another problem that uses a greedy algorithm with sorting and dynamic decision-making. Lastly, LeetCode 1353 Maximum Number of Events That Can Be Attended is an interval scheduling problem where assignments are constrained by time intervals. Understanding these related problems can help you build a stronger foundation for tackling assignment-based challenges. One common approach to solving campus bikes is the brute force method. Here, you calculate the distances for all possible worker bike pairs, sort them, and then assign bikes iteratively. This method has a time complexity of n squared asterisk log n due to the sorting step. While it's simple to implement, it can become inefficient for larger inputs. However, it's a straightforward way to start if you're looking to understand the problem or establish a baseline solution. A more optimized approach involves using a greedy strategy with a priority queue. By leveraging a min heap, you can dynamically process the closest worker bike pair at each step, avoiding the need to sort all pairs up front. This method also handles tie-breaking naturally and has a complexity of n squared asterisk log n due to heap operations. While slightly more complex to implement, it can be more efficient in practice compared to brute force. Another alternative is grid-based bucketing. In this approach, you group worker bike distances into buckets based on their Manhattan distance. This reduces the need for full sorting by focusing only on relevant distances. The complexity of this method is d*n, where d is the maximum Manhattan distance. This approach can be highly efficient for small grids but may become challenging to generalize for higher dimensions or larger inputs. Each of these methods comes with trade-offs, so it's important to choose the one that best balances efficiency, clarity, and adaptability to edge cases in the given problem constraints. Great job making it to the end. We've covered the solution to problem number 1057, campus bikes, and discussed key insights like the Manhattan distance calculation and optimization strategies. Remember to keep practicing and applying these concepts to similar problems. Thanks for watching, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!